Welcome to the video lecture by Dr. Biju Vasudevan for the course Calculus 3 Math 211. This is a first part of the video for week 11, in which we will see the chapter 3.5, which is the chain rule. In this section, we will derive versions of the chain rule for functions of 2 or 3 variables. These new versions will allow us to generate useful relationships among the derivatives and partial derivatives of variable functions. If y is a differentiable function of x, and we know that y is a differentiable function of x, and x is differentiable function of t, then the chain rule. So when you find the composite, you will find composition. You can write f of g of t, isn't it? And then it can be that we can find dy over dt, which is the derivation of the function with respect to t. When you substitute the x values in t, then y will be absolutely a function of t. Now you can find dy by dt. But in chain rule, we have seen it for a function of one variable. It is dy over dt, dy over dx multiplied by dx by dt. Isn't it? You can find differentiate with y with respect to x right here. Differentiate x with respect to t right here, multiply them. That is the answer here. This is the case for a function of one variable. We will now derive a version of the chain rule for functions of two variables. Assuming that here z is a function of two variables x and y, whereas every variable x is a function of new variable t. So remember, here it's given that z is a function of two variable x and y. And we know x is a function of a variable t, y is another function of a variable t. So when you differentiate z with respect to x, it is partial derivative dou z by dou x, because z involves two variables. There are two independent variables in z. We are derivating with respect to x alone, so it is a partial derivative. But here, when you differentiate x with respect to t, in this case, x with respect to t, it is total derivation, because x is a function of only one variable. So we should use the notation d over dt, dx over dt. So that's the difference between dou and d, dou by dou x and d by dt, isn't it? So here x is the function of only one variable. Only one independent variable involves, and we are derivating with respect to t, the same variable. So this total derivative dx by dt. But here z is a function of two variable x and y, two independent variables, and we are differentiating z with respect to x alone. This is partial variable, isn't it? One of the two variables. So dou z over dou x. That is this branch. The first branch is now dou z by dou x by dt. Multiply them together, and the second branch, come to the second branch of this tree. Here, if you want to differentiate z with respect to y, we will write dou z over dou y. Whereas when you want to differentiate y with respect to t, it is total derivative dy over dt. That is the difference between dou and the usage of the notation dou and d. Okay. So okay. Now multiply the elements in the first branch plus multiply the elements in the second branch. That gives the formula for differentiating z with respect to t. This is total derivative now, dz by, because now z becomes a function. When you substitute the values of x and y in this z becomes a function of only one variable. So multiply these two terms in the first branch, dou z by dou x multiplied by dx by dt, plus second branch dou z by dou y and dy by dt. This is the formula where here the inner variables x and y are functions of only one variable. Let's take an example. Simple example. Z is equal to xy, product of x and y, where x is t square, y is e raised to t. When you substitute the values of x and y in z, you will get z is a function of t. So z becomes a function of one variable. So when you differentiate z with respect to t, it is total derivative. That is why dz by dt is written here, right? So this is the formula for this case. That's what given in this table. In the theorem 13.5.1, this first formula is the same case what we have discussed so far. Z is a function of two variables, and every variable x and y is a function of only one variable. When we extend it for three variables, w, we use it second case formula number 6. Here w is the function of three variables, where x, y, and z are functions of only one variable. So we get one more branch, that is it. And the similar way, when every variable, every independent variable y, x, y, z are again functions of two or more variables. What's the case? That's the next theorem, 13.5.2. So for this theorem, before looking for this formulas, let's see the graph. This tree here, z is a function of x and y. There are two variables in z, and of course every variable, every independent variable for z, isn't it, is a function of two more new variables, u and v. So here v is also, y is also a function of two variables, u and v. Now we have four branches in this case, isn't it? So this plus comes here. The first branch plus the first branch, and second branch plus the second branch in this right. So okay, first, second, third, fourth, isn't it? First and third go together because the end variable is u. 2 and 4 go together because the end variable is v. So the question is it is a function of x, y, and x is a function of u and v, y is a function of u and v, isn't it? Now the question is, when you want to differentiate z becomes, even if you substitute the values of x and y in z becomes a function of again two variables. So when you differentiate by one variable, it is partial derivative. So it should be dou z over either u or v. Dou z over dou u, first case. Second case, dou z over dou v. So here the dark line shows the first branch and the third branch. Both are ending with u. Isn't it? So that is the case for writing the formula for dou z by dou u. Multiply the terms involved in the branches and then add with the third branch terms, isn't it? So dou z by dou x, dou x by dou u, plus dou z by dou y, plus dou y by dou u. In the similar way, you can write the second formula as well. So this is partial derivatives. We are extending the concept of chain rule for partial derivatives. Here, everywhere, that is all the terms involved in this formula are partial derivatives, because every variable is a function of two variables, isn't it? That is it. So the same concept can be extended for three variables, function of three variables. You can write w is a function of x, y, z, and you can write every x and y, x, y, and z can be a function of two variables or function of three variables. Is possible. So in this way, you can first draw the tree, and then from the tree the end variables should be considered. This ending with the u, then u and u will give you this. The branches ending with the u will give you the derivative of w with respect to u. So you can extend it for one more branch. If there are only two variables, x and y involves u. If x is a function of uv, y is a function of uv, z is a function of uv, then there will be one more. So this will be z, this will be w. You can try the same. The graph is given in this PowerPoint. You can check this one. Okay. So that's it. The graph is given here. Here w is a function of x, y, z, where every x, y, z are functions of two variables, uv, uv, uv. So there are three partial derivatives for w possible. Though w can end with this u, dou u, or dou w, dou v. U, there are three branches ending with u. This one, and this one. All the sum of all the three products will give you dou w by dou u. So dou w by dou v. There are three branches again. That's it. If there are again, if x, y, z are functions of three different variables, you can expand it. You can write one more branch here. That is up to you. Practice it. And this theorem 13.5.3 gives an idea to find the dy by dx. Finding dy by without implicit differentiation, we can directly use the formula, that is y prime is fx over fy, whereas fx is the partial derivation of f with respect to x and fy is the partial derivation of f with respect to y. So f prime, that means w prime, can be written as negative fx over fy. So this is for a function of two variables. You can write y is a function of x. This is actually, when you write in explicit form, it will be a function of one variable. Here the second case 13.5.4, when this equation defines z implicitly as a differentiable function of x and y. From this equation, if you can write z is a function of x and y, you can find the partial derivative of z with respect to x, partial derivative of z with respect to y by using this formula. This formula is nothing but negative fx over fz. This is negative fy over fz, where this subscript x, z, y all tell you that you have to differentiate by with respect to that particular variable. So these are the formulas of finding partial derivatives implicitly. Instead of doing implicit differentiation, directly use this formula. That is it. Okay, let's go ahead with the exercise set 13.5. There are two problems, so we'll choose one. Use an appropriate form of the chain rule to find dou z by dou t. This is what you are going to find. See problem number 5. Problem number 5. And from this one, you should have the idea. Z is a function of two variables, x and y, where x and y are functions of only one variable. We are in the first case, isn't it? Now, can you write the formula? So this term will be differentiate z with respect to x. This partial dou z over dou x. This is dou z over dou y. This is dx over dt. This is dy over dt, and both are ending with the same variable. So the formula you write here, it is what is it? dz over dt is the product of these two, dou z by dou x into dx by dt plus dou z by dou y into dy by dt. We have to find all the four terms from the given terms and then substitute in this equation. That's it. What is dou z? Dou z by dou x. Differentiate z with respect to x partially. What do you get? E raised to 1 minus xy. Derivative of exponential is the same, and then differentiate the elements in the power by using so when you differentiate 1, it will be 0, negative. Use product rule here for differentiating x and y. Keep x, differentiate y. This is now y is a function of differential function. So this would be dy by it should be partial. I'm sorry, this is actually when we are differentiating z with respect to x partially, y should be treated as constant. This is not product rule. So minus x, actually y is the constant. When you differentiate x, you will get 1. So this is negative y. The answer here it is negative y e raised to 1 minus xy. And we have to substitute the values of x and y in this equation. Then the term will be complete. So what is dou z by dou x? When you substitute the values of y is negative t cube e raised to 1 minus x is x is t raised to 1 by 3 and y is t cube. Simplify this one. You get negative t cube e raised to 1 minus t to the power 1 by 3 plus 1 by 3 plus 3. What is 3 into 3? 9 plus 1 is 10. T raised to 10 over 3. T raised to 10 over 3. 1 minus t raised. So this is an important term. Remember this one. And in the similar way, will you try to find what is the second term? Dou z over dou y. When you differentiate z with respect to y, it will be e raised to 1 minus xy, and when you differentiate with respect to y, 1 will be 0 minus x is constant. Keep it. When you differentiate with y, it will be x. So it is minus x into e raised to 1 minus xy. And of course here let this be equation number 2, and here we are going to replace the values of x. X is t raised to 1 over 3 and e power will be the same, isn't it? E raised to 1 minus t to the power 10 by 3. This is equation number 3. See, remember these two equations. We will need them for the next derivation. And we should not forget there is a negative here. This is a negative x. X is t raised to 1 over 3. Next, what we have to do is, we have already found dx, dou z over dx in this equation, dou zy. The remaining terms are dou x, dx by dt and dy by dt. That can be found from here. Dx by dt from the t is 1 over 3 t raised to okay, I will show it in the next page actually. From t x we will find dx over dt, which is 1 over 3 t to the power 1 over 3 minus 1, which is 1 over 3 t to the power negative 2 over 3. This is dx over dt. Another result, call it a. And when you differentiate y with respect to t, dy over dt, it is 3t square. Now let's recall the formula, which is dz over dt is dou z over dou x dx by dt plus dou z over dou y dy over dt. All these four terms are important, isn't it? First, dou z by dou x, we got it negative t cube e raised to 1 minus t to the power 10 by 3. Now dx by dt is 1 over 3 t to the power negative 2 over 3. Next term, dy over dz is negative t raised to 1 by 3 e raised to 1 minus t raised to 10 over 3. Okay, and multiplied by the last term dy by dt. Dy by dt is 3t square. We have to simplify all these things. The first term will be let's find the constant. The first term, what are the common terms? E raised to 1 minus t to the power 10 over 3 is the common term, isn't it? Now all the t powers you can see, this is 3t square, t powers. So there is a negative in common, negative is taken out. What else? This t powers inside. So this is t cube t cube into t raised to minus 2 by 3 in the first time divided by 3 1 by 3 plus t to the power 1 by 3 into t square times 3. So what is the power of t in both the times? Here it is 9 minus 2 7 over 3. Here 2 into 3 6 plus 1 7 over 3. So the t power is same. We can take out t power. So negative t to the power 7 over 3 and exponential 1 minus t to the power 10 by 3 all out. Now this is 1 by 3. The first time is just 1 by 3. Second time is 3. It will be 10 over 3. It will be 10 over 3. So that is the answer. That's the end of this problem. So in the similar way, try problem number 1. It could have been easier than this one. Next, use appropriate chain rule to find dw by dt. That is, I leave this to you. One function, so w is the function which is the function of three variables x, y and z. Again, all the three variables are functions of only one variable t. So you can write this formula dw by dt is, so this term is dou w by dou x, this term is dou w by dou y, this term is dou w by dou z. Dou w by dou x dx by dt, dou w by dou y dy by dt. The third term dou w by dou z and dz by dt. Find the terms from the given equation and simplify. I'll leave this problem to you. This one is a different because here z is a function of two variables x and y, where x is a function of two variables uv, y is a function. There are two problems, 22 and 17. Which is our choice? Which one you want me to solve? Let me choose problem number 22. Here both are of the same type. Here z involves two variables xy, whereas x is a function of u and v. Again y is also a function of u and v. So here we should write the formula carefully. If you don't remember the formula, just use this tree. Z is a function of two variables x and y, isn't it? That's what from the given equation. Now x is a function of u and v, u and v, u and v. Y is also a function of u and v. So there are four branches, and 1 and 3 are ending with u, 2 and 4 are ending with v. So whenever we find, there are two terms in the question, dou z over dou u, dou z over dou v. So when you are finding dou z over dou u, the first term, you involve branch 1 and branch 3. When you find the second term dou z by dou v, you involve branch 2 and branch 4. So can we write the formula for the first term? Dou z over dou u. Use the branches 1 and 3, which involves u, which is ending with u. So this term, this part, first part, z, derivate z with respect to x, that is partial dou z by dou x, since there are two variables. Again x has two variables, again partial derivation. This is dou x over dou u, dou x over dou v. This dou z over dou y over dou v, dou y over dou u. Use the first and third branches for the first formula. What is it? Dou z by dou x by dou u, plus dou z by dou y into dou y by dou u, where we are ending with the u, isn't it? So this is the formula for the first case. So let's write it. Now find all the four terms from this. You get this term by from z, And then let's find dou z over dou x from z. We will find differentiate z with respect to x partially. When you partially differentiate, the other variable should be considered as constant. Sin y is a constant term, isn't it? So differentiate cosine. It will be negative sin x, and sin y remains same because y is the constant now. And again from z find dou z by dou y. Now you are differentiating with respect to y partially, so keep x as constant. Cosine x will remain. When you differentiate sin, it will be cosine y. So we got two terms, first this term and this term. Obviously, what is dou x by dou u? Differentiate x with respect to u. X has only two variables, u minus v. So when you differentiate with respect to u, it is 1. The v is 0. And when you differentiate y with respect to u, what do you get? This is 2u. Just write all the terms in this equation number 1. So equation number 1 gives the first answer, dou z over dou u is negative sin x sin y, and then this is d dou z by dou x, first term. Next d dou x by dou u, which is 1, plus dou z by dou y, which is cosine x cosine y, and dou y by dou u is 2u. See, in the result there are 4 variables x, y, u, v. So we need to convert everything into u and v. The final variables are u and v, isn't it? So x is replaced by the value u minus v. Y will be replaced by u square minus v square. So final answer I'm writing here. What is it? Dou z by dou u is negative sin x is u minus v, and sin y is u square plus v square, plus cosine x is u minus v, cosine y is u square plus v square, and multiply this term by 2u. That's it. This is the first answer. Second answer is dou z by dou v. You have to do the same task with the branches from the graph. From the tree, use branch 2 and 4 to find second part, dou z by dou v. I leave this part to you. Try yourself. Now find dou u by dou x, dou u by dou y. U is a function of 3 variables r, s and t, whereas r is a function of x alone, there is no y, z. S is a function of y alone, t is a function of x and y. So try this one. The answer is also on the PowerPoint. Try this one. This is your practice problem. The same chain rule, you have to try all the problems, the similar type problems, and this is slightly different. In this model, actually we have to find dy by dx by using its direct formula. Dy by dx is negative fx over fy, where f is the derivation of the function, derivation of the function with respect to x partially, and derivation of f with respect to y partially, isn't it? And we have to check the result by directly using implicit differentiation. Okay, let's find problem number 39 or 40. 41. 41. Problem number 41, isn't it? this function we will write f of xy e raised to xy plus y into e raised to y minus 1, which is 0, right? So let this the negative one or positive on the left side and make it a function of xy. That is, now differentiate f with respect to x, dou f or dou x. So y should be treated as constant, so it will be e raised to xy. When you differentiate xy, you will get y. That is not product rule. You should remember, when we do partial derivative with respect to x, then y should be treated as constant. The second case, this is y, everything is in y, so second term is 0, third term is also 0. So first derivation with respect to x gives you y times e raised to xy. So this is the numerator fx. Now differentiate f with respect to y. You will get first, that is dou f over dou y. E raised to xy, when you differentiate xy with respect to y, you will get x plus y into e raised to y should be dealt with the product rule. Keep y, differentiate e raised to y plus keep e raised to y, differentiate y, it will be 1, and then negative 1 will be 0. This is the answer. This is fy. So what is it? E raised to xy times x plus y times e raised to y plus e raised to y. Isn't it? Therefore the answer is dy by dx, the numerator affects this term y into e raised xy with a negative sign. The denominator you will find x into e raised to xy plus y into e raised to y plus e raised to y. This is our answer. We can verify this one by direct implicit differentiation. What is implicit differentiation? Differentiate 41 implicitly. So you differentiate e power xy implicitly, isn't it? E raised to xy, derivative of e power xy is e power xy, and then open a bracket, differentiate this powers xy by using product rule. Keep x, differentiate y, this is y prime. Keep y, differentiate x, it will be 1 plus second term y into e power I using product rule. Keep y, differentiate e power y, that will be e power y. Keep e power y, differentiate y. So everything is done. Then when we are differentiating y with respect to x, it is y prime, and in the right side it is 1, so it is 0. So simplify, let's simplify this one. Let's take the common term, multiply this one inside, e raised to xy x y prime plus e raised to xy times y plus this term, let the second term be as it is. And now this term, from this term you can take y prime as common, so you get e power xy times x plus y into e raised to y plus e raised to y. Another term remaining is y times e raised to xy is 0. Now take this term to the right side, so x into e power xy, y into e raised to y, e raised to y, y prime is equal to negative y e raised to xy. Now y prime, this is dy by dx. dy by dx is y prime, which is negative y e power xy over x into e power xy, y into e power y plus e power y. This coefficient is in the denominator. So both answers are, equation number 1 and 2 are same. We have verified this one. And the last problem, what is given last problem? Find dou z by dou x, dou z by dou y by implicit differentiation, and confirm the results obtained. Okay, no need, just use implicit differentiation, no need to verify this one, right? What is it? Write the function as a function of two variable, and then you can write z as a function of two variable x and y. Okay, we will use both the methods here. First we will use implicit differentiation and then verify by using the formula. The formula from theorem 13.5.4 says that you want derivative zx, that is dou z by dou x, which is negative fx over negative f z. The similar way zy, which is dou z over dou y, which is this negative, this is positive, negative fy over fz. We can find by using this formula and then verify. I do this for zx, you try for zx. So now I am writing the function f y into e to the power x minus 5 sine 3z minus 4z is 0. So one function of three variables x, y and z. So now find derivative of f with respect to x partially. So other variables are considered 0. So y is remaining e power x will be e power x. Here second term only z, so it's 0. Third term is also 0. There is only z. So the answer is y into e to the power x. Now derivate the function with respect to the variable z, treating the other variables. When you differentiate with respect to z, the first term is 0, second term minus 5 sine will be cosine 3z and it will be 3 by chain rule minus 4. So this will be minus 15 cosine 3z minus 4. Now the final answer is zx. Negative fx is here. So negative y into e to the power x divided by this one. This term fz minus 15 cosine 3z minus 4. This is for zx. And we will verify this result by direct implicit differentiation. So implicit differentiation should be differentiated implicitly directly. So actually this is a function that involves three variables x, y, z. See, now you are differentiating it. So we are finding with respect to, so we have to consider is that, see, while implicit differentiation, it should be considered this is implicitly giving the function z as a function of two variables x and y, isn't it? Okay, that's implicit. So this is the explicit expression. It's implicitly given here in this equation. So we have to differentiate when with respect to x or with respect to y partially. So whenever we differentiate z with respect to x or y, you should write dou z by dou x or dou z by dou y. Now here we go, right? When you differentiate this one by product rule, you are differentiating with respect to x partially. Now differentiating with respect to x partially, keep y, differentiate e power x, it is e power x. Now keep e power x, differentiate y, because it will be 0 because we are differentiating with respect to x, then y should be treated as constant, minus 5, differentiate sine z with respect to sine 3z with respect to z, with respect to z, then z with respect to x, the chain rule, isn't it? It is cosine 3z and then this 3, the constant by chain rule, then z dou z by dou x. In the right side it is 4 times dou z by dou x. So we need to club the terms that involve dou z by dou x together. This term is 0, this term the right side, so negative 5 cosine 5 into 3, 15 cosine 3z minus 4, this right hand side, 4 in the left side. The coefficient of these two terms is dou z by dou x, and this term y into e raised to negative x in the right side is negative y into e raised to x. Now you get dou z over dou x is negative y e raised to x. This term in the denominator, it will be negative 15 cosine 3z minus 4. That's the end of this problem, and try the similar type problems from the PowerPoint. Thank you very much.